Today we're going to revisit resistance to changes in motion, not in terms of inertia. Instead, we'll introduce a new concept called momentum. Momentum is a measure of an object's quantity of motion. And this quantity of motion can be transferred between objects through collisions. An easy way to qualify how much momentum an object has is as a measure of how hard it is to stop the moving object. Football is a good example of this. The bigger a running back is and the faster they're moving, the greater their quantity of motion, the more momentum they have, and the harder it is to bring them to a stop. There are two types of momentum, linear and rotational, but for now we'll just focus on linear momentum. Linear momentum is equal to the system's mass multiplied by its velocity. Two weird things about momentum. First is that we use the letter P to represent it. I don't know why, you don't know why, nobody knows why. And it has units of kilograms meters per second, but for some reason they don't simplify that into its own special unit. Because it's found using velocity, momentum is a vector quantity, so we have to be careful about the direction of our velocities. Let's briefly revisit Newton's laws. These laws were actually originally written in terms of momentum. From the first law, we know a force is needed to cause an acceleration. So, force is required to change momentum. The second law told us that force is equal to mass times acceleration. But in terms of momentum, force is equal to the change in momentum over the change in time. So we can say that force is the rate of change in momentum. The third law told us about how action-reaction forces work. These forces are equal and opposite. So if we sub in Newton's second law in terms of momentum, notice the time will be the same, since when two objects collide, they have to interact for the same amount of time. So the times cancel, and we're left with the change in momentum A is equal and opposite to the change in momentum B. This shows us that all momentum changes when two objects interact are equal and opposite. And as long as no net force acts on the system, we can say the total momentum of the system is conserved. So the total change of momentum in a system is going to be 0. Let's take a look at a practice question. The cart's change of momentum is, so we have a 10 kilogram cart traveling to the left at 2 meters per second. It bounces off a wall, collides with the wall, and bounces back at 1 meter per second. And we know what the change of momentum is. So momentum is mass times velocity, but remember that momentum is a vector quantity, so the fact that the 2 is going to the left and the 1 is going to the right, that's going to be important. So generally, when an object interacts with something else like this, its mass doesn't change, only its velocity. So its change in momentum would equal its mass times the change in its velocity. Now, since this cart starts by going to the left and then bounces back to the right, we know overall its change of momentum has to be positive because it resulted in a momentum to the right. So that means these first three choices can be eliminated. The cart can't have a negative change in momentum. So let's find the actual change in momentum. Let's find its change in velocity first. So we'll do final minus initial, so 1 meter per second, which is positive because it's going to the right, so positive 1 meter per second, minus negative 2 meters per second. 1 minus negative 2 is 1 plus 2, which is 3. So its change in velocity is 3 meters per second multiplied by the mass of 10 kilograms. That gives us 30 kilograms meters per second.